How's it going? I am feeling better. Thank you for asking. Hmm. Hope everyone's having a good day. Feeling better. I'm not as well rested as hoped to be, but insomnia is a crazy thing. So we'll get through this. I'll get through this. All right, so I'm going to pick up where I left off from the previous lecture, which, since I didn't lecture in this class, when I say the previous lecture, would be the Monday lecture, which hopefully everyone checked that one out and was able to get caught up. Um, that one, actually, there wasn't a whole lot of interactivity, if I recall, because a lot of it was just definitions and examples trying to illustrate the definitions. And so today we should have a little bit more things to look at overall. So. So we're going to look at basically the continuation of section 2.1. So at this point in section 2.1, we've looked at just the basic concepts. Okay, here's a set of data. Let's create a bar graph or a Pareto chart for this categorical or qualitative data. Now, I did not get to a couple of things yet in this section, so I think we'll begin with a few more definitions, which will be relevant for section 2 when we look at quantitative data as well. So with definitions, we have three of them that we have to introduce here. We have frequency. Now, frequency is the number of times that each response is given in a data set. Okay. And so if I asked everyone in class, what is your favorite type of music to listen to, then maybe 5 people in class would say hip hop, maybe more than that. I don't know where things are nowadays. There's a lot of blurring of the lines between different music genres as far as commercial things. Anyway, but that would be the frequency of that particular response. If 5 people chose it, then it has a frequency of 5. So basically, the number of occurrences, number of times that each different response is given. Next, we have sample size, which I probably should have. No, I feel like maybe I should have mentioned this one sooner, but we really haven't had to worry about it until we get to this point. Now, sample size is the total number of data values that are collected, or total number of let's say the number of individuals in the sample. That might be a little bit more accurate. Okay. And finally, we have what's called the relative frequency, which is a ratio that shows the proportion of, maybe I should not say proportion. We could say, yeah, proportional work. We could say a ratio that represents the proportion of individuals I'm off the screen, sorry. Represents the proportion of individuals that selected a response. I think I like that definition better than the one I gave in my other class. Yeah. Anyway, basically, if we have a class of 30 people, and let's say 6 of them have their favorite color is blue, then 6 of the 30 people in class, or that works out to be 20%, would that means the relative frequency of blue as a favorite color is 20%. So the way that we calculate relative frequency, first of all, frequency, we usually use the letter F to represent. Sample size, we actually use the value N to represent. And so the relative frequency, or F, is calculated as F divided by N. And we'll look at this in more detail with an example about how we would actually set up this table. It actually will be a table where we list out the different responses, the frequency of each of those responses, and also the relative frequency. Okay. So we'll get to why this is the approach that we use, or which this is the formula that we use in a moment. Okay. So, um, for this problem, I think we'll go ahead and look at problem 14 on page 72. Or for this topic, I mean. No, this is the problem. Oh. Move to the next page. Right. In a national survey conducted by the Centers for Disease Control to determine health risk behaviors among college students, college students were asked, how often do you wear a seatbelt when driving a car? The frequencies were given as below. And so we have 6 different responses that were given, and we already have the frequency provided as well. So I'll go ahead and just write this down as a table. So we have frequency, and we want relative frequency also. So the different responses to the question, do you wear, or how often do you wear a seatbelt when driving a car? So potentially respondents may not actually have a car to drive. So that's our one response, no car. Some that never wear a seatbelt. Some that rarely wear a seatbelt. We also have sometimes, most of the time, and of course all the time. Now, there are 249 people that do not have a car, 118 that never wear a seatbelt, 249 that rarely do, 345 of respondents sometimes wear seatbelts, 716 most of the time, and then 3,093 all the time. So that's the information that we've been provided in this particular question. Now, remember that I said to find the relative frequency, we need to take the frequency and divide it by the sample size. How do we figure out how many people were surveyed to get these responses? What is our sample size is basically what that amounts to. Does anyone know how we could do that? Add up all the frequencies, exactly. Yeah. So I want to take each of these 6 numbers and add them together. Now, in some of these questions, we'll actually see that this number is given to us as part of the question. Like maybe the question says we surveyed, 100 people that have this criteria. Here are their responses to this question. This one does not provide such a courtesy, so we will need to add all 6 of these numbers together and figure that out. Okay. 249, 118. 345, 716, and 3093. So 4,770. So that's N. That's our sample size. Now, the relative frequency, and this should help illustrate this a little bit better. The relative frequency, we said, was the proportion of the total that each response represents. So we know that 249 people don't have a car, but maybe that's not a great way to represent that, because okay, it sounds fine to say 249 people don't have a car, but how do we put that in context for the people who are looking at our results? How do we help them understand, like, what does this actually mean in terms of maybe the overall population? And so what we want to do is calculate this relative frequency. So we said the relative frequency would be the frequency divided by the sample size. So we have 249 over 4770. Now, that's going to give us a decimal value. Now, there's multiple ways we can represent the frequency. Technically, we could leave it as, the relative frequency. Technically, we could leave it as a fraction and maybe reduce that, but fractions are not the best way to convey relative size of these different responses. Generally, we would like to use either a decimal value or convert that decimal into a percentage. Now, the other issue is we have this term here that has a lot of different numbers after the decimal, and so the question is, how far do we go in expressing this as a decimal or as a percentage? What I would recommend is either 3 or 4 decimal places. In this case, I think 3 is acceptable. We shouldn't need to go any further than that unless the data is unless the numbers in the data that we get are small enough that we need to go further to separate them from each other. That's basically what that amounts to. But we shouldn't usually have that situation where we need more than 3 or 4 decimal places here for relative frequency. So if we just go to 3 decimal places, we would do 0.052, or that could also be called 5.2% if we convert that to a percentage. And again, you could either leave it as a decimal or write it as a percentage. Both of those equally convey the relative size of each response. So 5.2% of our group does not own a car, therefore the question is irrelevant whether they wear a seatbelt while driving. And so we repeat that for each of these different responses. 118 over 4770. That gives us, let's see, if we round to 3 decimal places, what would that be? So again, if we round that to 3 decimal places, what would we get there? 0.25. Good. And again, that would be corresponding to 2.5%. Okay. Yeah, we have a 7 as our fourth number, so that would round our third number up to a 5. We round that, yeah. Okay, now we actually have the same number of people that chose rarely as chose no car. So the result will be the same here, 0.052 or 5.2%. Sometimes is 345 divided by 4770. So that's 0.072. Or 7.2%. Mostly. Will be 0.150 or 15.0%. And always, this should be the biggest one because we have the largest frequency. Looks to be about 648, so 64.8%. Okay. Without adding these numbers together, what number or what value do you think the relative frequency should add up to? %100? Or 1. Yeah, the decimal values should add up to 1, and the percentages should add up to 100%. Right. Now, if we actually add these together, let's see, that's 9, 19, that's a 9. So carry the 1, 6, 7, 8, 13, 20, 35, and 64 is 99. We add that up and we get 99.9% or 0.999. Why would we not quite get 1 in this scenario? Can you think of a reason? Right, it's because of the rounding, and it just depends on how many more terms that we rounded down as opposed to the ones that we rounded up. And so because of that, it's going to give us a sum that's slightly off from what we normally would expect to see, 1 or 100%. As long as it's not off by much, and it shouldn't be, then that means we've done everything correctly. So it should still be, it should be within, like, in whatever our last place is here, the thousandths place. That's where the difference should exist. If we have a difference here in the hundredths place, like we had come up with, instead of 999, if we came up with 979, that means we've really missed something here, or we miscalculated something. We shouldn't be that far off. We shouldn't be off by more than 1 or 2 points on the last digit. That's generally we're going to find. So it could be 1.002, and that would be acceptable. That would be an acceptable rounding error that we won't have to worry about. But if we added this up and we came up with 97%, then there's definitely an issue there, because we should not be that far off from the actual answer. Yeah. Okay. That was part A of this problem, is to take this data which is provided and then figure out what's going on in this last column with the relative frequency. So part B, now that we have all of this, what percentage of respondents answered always? So always, we can certainly just look that up and see it's 64.8%. Now question C here, what percentage of respondents answered never or rarely? Now they've given us two different responses that we're interested in. What would we need to do with those values to come up with our answer to this question? So how would we find the percentage that selected never or rarely? Add them, right? Yeah, so we just take the two responses and add them together. Never was 2.5%, rarely was 5.2%, so if we add those together, that's 7.7%. Okay. Now, they want us to create two different bar graphs here, one for frequency and one for relative frequency. I want to skip the frequency bar graph here because honestly, with this many individuals participating in the research, the frequency by itself does not really convey a lot of meaningful information, and that's why we calculated the relative frequencies. We could say 3,093 people reported always wearing a seatbelt. And you know, as responsible viewers of statistics, our first response to that would be, that's great. How many people are actually in the study? How meaningful is that 3,093? So if we said, hey, that's 300, that 3,093 represents 64.8%. Now we have some context for that number. Now we understand that a lot of people do wear their seatbelt, but it's actually less than 2/3 of the total, which potentially is a problem from a safety standpoint. So that's why the relative frequency is important, because it does provide context. So we could say that a police department in California, let's say, had their budget cut by $20 million. Okay, that's great, but what does that mean? What does that tell us in reference to what they were already getting? If the department was already getting $500 million, then $20 million loss is not a huge amount. Okay. Anyway, so it's always nice to have context with these numbers. What does this actually indicate? You know, as far as what does it tell us about the problem? So sometimes the frequency, which sometimes we'll call this the raw data, doesn't give us the context that relative frequency does give us, and that's why we like to incorporate it. Okay, so let's look at question E, where they want us to make a relative frequency bar graph. and I'm going to not have room in this page. I'll move to the next page. All right. Sorry, we're not talking about histograms yet. We're talking about bar graphs still. Histograms is the next section. That's my bad. It's almost the same thing, but it's a little bit different, and so I don't want to get into that just yet. The way we construct our graphs, again, we have a vertical axis and we have a horizontal axis. Now, on our horizontal axis, we'll want to write each of our different responses. So we have 6 responses. We'll go and make 6 marks here, try to equally space them. So we have no car, never wears a seatbelt, rarely, sometimes, most of the time, and always. Okay. Now, if we're looking at the relative frequency, again, we can use percentage or we can use decimal. Let's go ahead and try to use percentage here. Now, I was able to make 10 marks going up on this side. What would be a good, and again, we want to make sure our numbers are equally spaced. What would be a good number to count by here in order to properly show the differences between the data values, the nuances here? So what I'm asking is, what value should this first mark be when we create this bar graph? 10? We can certainly do 10, and so we do 10, 20, 30, 40, all the way up to 100. One problem with that, with 10 is not a bad answer, but we look at our data values, and 4 of the 6 values are less than 10. Do we have enough room to properly show the differences between those values? Maybe, maybe not. So we might think, okay, what if we use 5 instead? Yeah, because that would be our next thought. And here's the issue with 5. I have 10 marks here. So we start counting by 5, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. The top of our graph ends at 50%, but our largest value is actually 64.8. Okay? And so it wouldn't even be on this graph. Now, this is kind of a silly question, because then we would say, well, we could just make a taller graph, which is correct. We wouldn't necessarily be restricted by what we've sketched here. But that's something to think about, is how close together do we need our different marks here to be able to show differences between these different numbers that we got as a result. And so I would say ideally we'd be able to count by fives. The only issue is our graph is not tall enough for that. So we could potentially count by sevens. Seven's kind of a weird one though when you think about decimal values. 5 and 10 make a lot of sense. 7 doesn't really make a lot of sense. So if we were to use 5 or 10, we would have to 7 makes sense, but in a way it does, and in another way it doesn't, because it's just such an unusual number when we're working with percentages to count by 7% rather than 5 or 10. So if we had to choose between 5 or 10, we would probably just go ahead and use 10% increments. But the reality is 5% would be better, and we would just take the time to make our graph taller in that scenario. Especially if we're using software such as Excel or similar spreadsheet type software where we can just move the data down on the page and then increase the height as needed. So anyway, ideally we'd be counting by fives, but we don't really have room for that. So I'm going to go ahead and count by 10, which again doesn't necessarily feel right, but there we are. That's an 8, sorry. Okay, so no car was about 5.2%. Never was 2.5%, so about half that height. Rarely 5.2%. Sometimes 7.2%. Mostly is 15. And always was 64.8, about 65. Okay. Now, if we've been able to sketch this properly, and again, this is just a sketch, so ideally we would have some kind of software producing this graph for us, so the relative differences between the bars are accurately shown on the graph. We're just freehanding it, so we can accept that there's going to be some things that maybe not look quite right, but as long as we do the best we can, it's fine. So this is our bar graph. If we wanted to make a Pareto chart, which two responses would be listed first? Oops. Always and then mostly? Correct. Almost exactly the opposite of what we have. That's right. Yeah, because in the Pareto chart, we arrange the bars so that they go from highest to lowest. So our highest bar would be always, that would be first, then mostly, and then sometimes. Now, no car and rarely actually have the same relative frequency. Um, so if they have the same value, then we can basically use whatever order we feel works best, whether it's alphabetical or if we think there's some better ordering that works, and then never would be last. All right. Any questions on this? All right. Let's see. I think that just about does it for that section. We're doing okay on time. So let's move on to section 2.2. And we won't be able to finish section 2.2 today, but we'll at least get started. Sorry. Okay. Let's do that. Section 2.2 is on organizing qualitative data. There's one other thing that I didn't mention with the categorical data, and that is that we could also use a pie chart there. I'm not going to draw any pie charts though, so I mean, and I figure you already have a pretty good idea of how to do that anyway, so we were just going to focus on the bar graph there for section 2.1. Now for 2.2, we're going to look at a couple of different displays. The histogram is one display that we'll have here, which is basically a bar graph, but there's a few unique characteristics that we have to include that make it a histogram, and those are strictly used in the case of qualitative data. We also will look at what's it called, a stem and leaf plot, and we'll talk about that a little bit more. Actually, I don't think we'll get to that one today. We'll probably talk about that one next time, and maybe one more. We may or may not talk about a line graph or a time series graph. I probably will show you in the book some of these other types of charts, but we won't necessarily utilize them ourselves. So, okay, but now we're looking at organizing qualitative data. Now remember, qualitative data, we had two subcategories there, discrete and continuous, that we talked about back in chapter 1. Discrete data is countable, so we're counting 0, 1, 2, 3, 4, etc. And continuous data could have all kinds of different values, decimals and fractions or whatever. Now, for discrete data, we actually have a couple of different choices as far as how we can represent discrete data on tables, basically creating a relative frequency distribution table. as far as continuous data goes, we really only have one choice. But let me give you an example. Let's start off with the data set. And for this data, and I'm just making this up, I'll tell you right now. This will be the number of siblings of statistics students. Which I don't know how scientifically meaningful any that kind of research would be. I'm just making something up that we can easily work with. And so I'll just give us the raw data first of all, and I'm going to go ahead and pick 20 different values. Okay. So we have 20 different values here, and we can see the smallest one is 0, so we have several only children in the class. We have a lot of people with one sibling, so they have there's 2 children in the family. Others with 2, one with 3, one with 4, and one with 5. In fact, for the purpose of this, I would actually like there to be, let's say this was a 3 instead of 4. I'm sorry about that change. I may have enough room here to do this, but we'll see. There's our data. Okay, and we want to create our distribution table, so we'll have our response, different responses, the frequencies, and then the relative frequencies. So we look at our different responses here. Our lowest one is 0, and our highest one is 5. Now, we want to make sure on qualitative data, even if there's a certain number that's not present in the data or in the list of data given, we want to make sure our responses are listed from low to high with each value possible in between. So even though we don't have anyone with 4 siblings in this group, then it doesn't mean that no one has 4 siblings. It means in this group we don't have anyone with 4 siblings. Okay, so let's look at frequency. What is the frequency of 0 in this list? 7. Yeah, 0. There's seven different students that have 0 siblings. What about 1 sibling? That appears to also be 7. Is that what y'all got? Yeah. I didn't intend to make those the same, but it's okay. How many with 2? Well, that's a little bit easier. There's 1, 2, 3 responses have 2. How many with 3 siblings? Just 2 of those. How many with 4? There aren't any with 4. And 5, of course, is just ones. Now, we know that this frequency column should add up to 20 because I told us at the outset I was going to use 20 responses. But we can double check that, make sure we've counted everything properly by adding these numbers together. So even though we know it should be 20, it's nice to go back and check just in case. 7 and 7 is 14. 3 more makes 17. 18, 19, 20. Okay. So again, we're going to divide each of these by 20 to get the relative frequency, and let's write it as a decimal in this case rather than a percentage. So we'll do 7 divided by 20, and so that comes out to be 35%, or 0.35. I already went back on what I said. So 0.35, and that's the same. 3 divided by 20 will be 0.15. 2 divided by 20 is 0.10. Still have 0 for 4. And then 1 divided by 20 is 0.05. And that actually that actually adds up to exactly 1 because there is no rounding there. That's one of the reasons I like working with 20 data values, is that the relative frequencies are all exact values. Unfortunately, the real world is not perfect, so we frequently end up not using exact values there. So, everyone okay with how that table was created? Or, I mean, let me know if you do have any questions there. Now, this particular table that we created, we refer to that as an ungrouped distribution table because the responses are not grouped together, which kind of tells us what the alternative is, which is to use groups. And depending on what our data looks like, because we only had 6 different numbers given here, it was easy to list them all out. Actually, we only had 5 different numbers, but technically the 4 was in between, so we had to include it. Now, with grouped distributions, that means we have so many different responses, we can't actually list them individually. Yes, we can use either decimal or percentage. I just chose to use decimal in this case. Okay. Now, let's go ahead and I mentioned histograms. Let's go ahead and define that before we dive into that, and basically show what are the differences between a histogram and a bar graph specifically. Now, a histogram is a type of bar graph that is used for quantitative data. And where responses are arranged in numerical order from low to high on the horizontal axis. And the bars are adjacent to each other. So when we say adjacent, that means the bars will actually be touching each other. There won't be any space between them, unlike what we did with the previous graph, which. So with our just our bar graph with categorical data, we left the bars separate from each other. Now with the histogram, these bars will be right next to each other, sharing one side between them, basically. Okay. So let's see. Our data was number of siblings of statistics students. This will be the title for our graph. Almost going off the page. Okay. Could have drawn a straighter line. I apologize for that. It's all weird now. Let's continue. So on our table, we came up with 6 different options. So we will list them down here. So 0, 1, 2, 3, 4, and 5. So this is siblings. And in this case, because the data is small enough, we could use frequency, because we only have 20 data values, so frequency is a possibility here. As far as what we use on this vertical axis. In fact, the largest one was 7. So we just need 7 marks here. Okay. So 0 had a frequency of 7. Okay. 1 actually also had a frequency of 7. 2 had a frequency of 3. Okay. So notice when I'm constructing these bars, basically I'm drawing the vertical line halfway between the two numbers. This is the line that they share. So like here, between 1 and 2, I drew this bar, and so I just constructed the next one off of that. 3 had a frequency of 2. There we go. 4 had a frequency of 0, so we'll actually have a space there in the graph. And then 5 had a frequency of 1. Okay, so that would be our histogram for the number of siblings for stats students. Okay. Any questions about the histogram? Okay. Now, that's ungrouped data. So going back again to our table, we only had 6 different responses. Well, we had really 5, as we said, but it was easy just to list those out as our responses, and then find the frequency of each, and then calculate the relative frequency as we do. Now, ideally, we wouldn't have more than maybe 10 values there, and ideally less than that. It just depends on what it is that we're looking at. So our alternative is, if we have a lot of data that has different values, not just a couple of values that are predominant like we have here, then in those cases we like to use what's called a grouped frequency distribution. So let's talk about that next. So this will be useful when we have a wide variety of data values present in the set, or in the data set. Specifically, when we have more than 10, we would definitely want to use a group frequency distribution, especially if it's a lot more than 10. Because we don't want to break up our ideally we have 10 categories or less, unless the nature of the responses lend itself to more categories. When we look at a common example is age groups. If you look at ratings for television shows, which I guess is still a thing, they probably include streaming numbers now. But they usually break it up by age groups, and then we can see which age groups prefer which shows more. And if there's like an age group that's being underrepresented, especially age and gender combination, then you can see that there's a need for more shows for that particular group, theoretically. It may not be a lot of demand. That's another issue entirely. But anyway, when we talk about ages, if we take a poll of 1,000 people at random, we're going to get a lot of different values for people's ages there. So it's really inefficient to list them all out individually, and so we prefer to use groups in this case. So for age groups, we might see under 10 to 19, 20 to 29, 30 to 39, and we would keep going from there. And that would be our groups that we use, and we basically go through and say, okay, how many people polled were in this age group, how many people were in this age group, how many in this age group, so on. And that would be our frequency then. Okay. When we create our groups for the group frequency distribution, there should be no overlap between the groups. Because if we have a respondent that is aged 10, then we know that they go in the 10 to 19 range. If we have a respondent that's age 29, they're in the 20 to 29 range. They're not in the next one there. So the groups do not overlap. The other thing that we want is that groups should be and should have equal width. Okay. So that brings up the topic of the class width. So another word for these groups is classes. And that's probably the more accurate or more commonly used name is classes. And so the class width this is the distance from the lower limit of one class to the lower limit of the next class. And I'm off the page. Sorry. Okay. So class width is distance from the lower limit of one class to the lower limit of the next class. Now, when we say lower limit, that's the first number of each group, and the upper limit would be the second number in each group. And technically, it doesn't have to be lower limit to lower limit. It could be upper to upper. So, for this group 10 to 19, and this group 20 to 29, what's the class width? What's the difference between those lower limits? Ten? Mm-hmm. Yeah, so basically we're counting by 10. When we say under 10, that would technically start at 0. So 0, 10, 20, 30, and then 40 and 50 and so on. And under 10 it would actually end, it would be 0 to 9 if I wrote it up properly. And then the same class width should be demonstrated as the difference between these numbers on the upper limits. So from 9 to 19 to 29 to 39 and so on, those are all 10 units apart also. And in order for this to be a proper group frequency distribution, we would prefer that each group have the same class width. Frequently, when you see age distributions, you might see like under 18 as one group, where they're legally identified as children, from 18 through maybe 34, 35 through 49, and then 50 plus, and that gives you a lot of different class widths there. The widths are not consistent from one class to the next, but that's what we frequently see in some of these age breakdowns, because that's just what's been used, I guess, for years and years. For a proper statistical research, we do want to have those equal widths between each class. Okay. So the class width, the way that we calculate this is equal to the maximum data value minus the minimum data value divided by the number of classes and once we calculate this result, we'll then round up. Okay. We'll talk about why in a moment. Although we don't have too much time left, this may be the last thing that we do today. Let me go ahead and put down another data set for us to look at. Let's see. This is a data set I used in my other class. Actually, I've used it in previous semesters. I had a picture of my board back when I was in the classroom before all this happened. It was just a good set of numbers, and I just wanted to use it again. So this data is ages of stats students in an evening class. And I specified an evening class in particular because we tend to see, from my own experience, we tend to see a wider range of ages in an evening class versus a daytime class where it's largely what we call traditional college age, which is 16 to 24-year-olds. Normally I would say 18 to 24-year-olds, but then we also have people from early college, high school, which takes that number down a step or two. Anyway, evening classes, we tend to have a wider age range because we have people who are working full-time and then come into class at night. Also have people that work overnight and they'll come to class before they go to work, which is sounds insane to me, but I mean, I certainly respect them doing that. So, anyway, so for this data set, again, is 20 values. I like this number as an easy number to work with. It makes the data set something that we can work with just by hand, basically, if we needed to. And we can do it in a relatively nice amount of time. I once had a student in class that was 91 years old. It's her lifelong dream to get a college degree. And so, good on her. I don't know that I'll have the same ambition when I'm 91. Anyway. So, here's our data set. What is the maximum value that we have listed here? $45. And our minimum $18. Good. All right. So now, oh, it's on the other side of this page. Sorry. I said for the class width that we would take, and I'll just say it, we would take our maximum value minus the minimum value and divide by the number of classes. Now, the question is, how many classes would we use for this? Potentially, we could use, for 20 data values, we certainly wouldn't want to create 10 classes, because that would be like 2 people per class on average. And we would probably have a lot of empty classes in that scenario. So we might go for something a little bit less here, and I'll go ahead and say let's use 6 classes in this scenario. This is something that I will go ahead and tell you anytime I give you a problem like this, so don't worry about trying to figure out how many classes we have. I'll go ahead and tell you what to do there. That answer requires a little bit more experience as far as knowing what number would be good to represent this particular data set. It really just depends on how many different data values we have and the range of data values we have, which is the difference between the minimum and the maximum, basically. But we definitely wouldn't want to go higher than 6 here, and we may even want to use 5 instead, but I'm going to stick with 6. Okay, so we set our class width as our maximum minus the minimum and divide by the number of classes, which are using 6. So we would want to take 45 minus 18 and then divide by 6. Now 45 minus 18 is 27, and if we divide that by 6, oh goodness, we're running out of time here. We get a, what is that, 4.5? And so we'll round that to 5. Now, even if we got like 4.2 here, we would want to round it up to 5, because as I said before, defining the width, we want to always round up. And the reason we want to do that is that, based on what data we have here and like the numbers that we have, 4.5 is exactly the number of classes we would need, or the width we would need to make 6 classes. Any less than 4.5, and we would have we would end up trying, when we try to put our numbers into these classes, they wouldn't fit. Basically, we'd end up with values that didn't fall into any of the classes we had. So we would actually round up in that case, make sure it's 5. Unfortunately, we've really reached the end of our time here. I'm going to come back to this example and we'll continue with it on Tuesday next week. But for now, I'm just going to assign you one homework problem from section 2.1. This will be number 15. And I just want you to do parts A, B, C, and D. And if you would, go ahead and do a Pareto chart. Which is not one of the questions, but I want you to go ahead and try to make one there. So, alright, kind of kept us all the way to the bitter end. We do have a holiday on Monday that doesn't affect us, but I hope you enjoy the long weekend. I hope you are able to enjoy the long weekend. I hope you're not working the full time, unless you really need the job. But hopefully you get some time to enjoy the day off that we have. So everyone take care and enjoy yourself, and I will talk to you Tuesday. Have a good one.